Hello everyone, this is Mentonto coming to you to present a technical sciences topic, electrostatics. I hope this topic will assist a whole lot of learners to perform better in the topic. Thank you. Without any waste of time, I will start my presentation. The first thing that I'm going to address is the prescribed content for this particular topic, electrostatic. We are going to deal with capacitors. Now, learners should be able to define a capacitor and give examples of uses in technology. Define capacitance and capacitor and use this formula C equals to Q over V in the calculations. Also express capacitance as C equals to E naught A over D. I will explain these symbols in the formula as we go on, and also use that formula in calculations. We will continue with capacitance calculations, and lastly we'll discuss all the factors affecting capacitance. Right. Now, this is a concept map for capacitor. We are going to look at definitions, and under definitions, the capacitor, capacitance, and also you can also include the dielectric, a definition for dielectric. We are going to look into dielectrics, advantages of using dielectric, and also atomic view of the dielectric, types of capacitors, also connections of capacitors, how they are connected in series, in parallel, and the combination of thereof. These are important terms that learners should be able to define as is. And what you should take into consideration is that when you define concepts, make sure that all the key words are there and the context of the definition is correct as defined in the Free State Assessment Guidelines. Right. The definition for capacitance is the charge stored on the plates of the capacitor per unit potential difference between the plates. And in symbols, it is denoted by C, which stands for capacitance over charge over potential difference. Capacitor, an electronic device that stores electric charge and energy. Now, charging, what does charging by induction mean? It means it is a process in which an object obtains a charge without being in contact with a charged object. A dielectric is an insulating material placed between the plates of a capacitor. An insulating material tells you that it does not conduct electricity readily. Now, parallel plates is a device that consists of two oppositely charged conducting plates separated by a small space in between. Right. Then let me just show, as they define capacitors, to show you types of capacitors that we are going to be faced with. This is how we indicate a capacitor. These are it's a capacitor in between. There will be a dielectric material in between, but now a symbol that indicates a dielectric. These two lines separated by a distance in between with the conducting wires. This stands for fixed. It's a fixed capacitor. Then we have a variable capacitor, same as that one. Separated by a distance in between connecting wires and that arrow running through. This one is a variable capacitor. Variable capacitor. Right, let us continue. Now let us look at formulas that we are going to be using in the calculations thereof. The first formula is C equals to Q over V. As I indicated, C stands for capacitance of a capacitor, Q a charge, and the capacitor and capacitance is calculated in farad. And a farad is a big unit, so normally you'll find that in microfarad or picofarad it will depend on a situation or on a problem that you'll be given. So it means you'll have to convert a microfarad to farad so that you substitute in correct SI unit. A charge, Q stands for charge, and the SI unit is coulomb. V stands for potential difference, and the SI unit is volt, denoted by a capital V there. Then we have another formula to calculate capacitance, where now areas of the plates are taken into consideration. The formula is C equals to epsilon naught A over D. A stands for area of the plate, and area, we calculate area in meters per second, because area of a plate will be length times breadth. That is m by m give you m squared. Therefore, distance is D stands for distance and is calculated in meters. Epsilon naught or E naught is permittivity of free space and is a constant, and the value thereof is 8,85 times 10 to power negative 12 farad meter per meter. So now this value on the formula sheet, when you are given a question paper, it will be given to you. You can copy it directly from the formula sheet. You don't have to memorize it, but know it. Copy it correctly from the formula sheet is going to be given to you. And the formulas as well. Both formulas do appear on the formula sheet. The last formula is still the same as above. The only difference is that it has now an addition of relative permeability of the free space, K, and it does not have an SI unit. So this is the value of the dielectric, the strength of the dielectric used between the capacitors or between the plates. Right, therefore, epsilon naught, we have already talked about that. Therefore, as indicated, these values you'll be given on the formula sheet: the permittivity of the free space and relative permittivity of the free space, or also a K, it will be given to you. Right, you should keep all of these formulas in mind, symbols and their SI unit, because it is important. When we do calculations, we should never forget that at the end, when you write your final answer, the correct SI unit must be shown. And if not, you will lose marks. Now, as learners or candidates write exams and all of that, reports are gathered on the common errors and misconceptions that they do. One of the misconceptions is that candidates tend to omit keywords, like when defining a capacitor charge, they will define it with and omit that keyword. So make sure that when you define, you do not leave out the keywords. Candidates have misconception between the relationship between the capacitance and the charge. We are going to look into that and clear up that misconception. And also candidates are unable to indicate the charge on the plates. Instead, they give answers like increased the distance between the plates, decrease the surface area, and use small dielectric material. So we need to elaborate on that. We will go through those so that we address all of these errors and misconceptions. Electrostatics, we are going to look at the following: capacitors, examples of capacitors, capacitance of the capacitor. There's also factors affecting capacitance. We're going to look into that. So here we see there are different types of capacitor, different types and shapes. There are cylindrical ones, there are circular ones, rectangular ones, and all of these capacitors are used in different applications in the electronic devices. And on the motherboard, you will see all of these in the alarms. There are so many applications. We'll look into that as we go on. This is just to show you how a capacitor looks like. As you can see, remember when I drew a capacitor, I indicated the terminals. It also has the connecting wires there. Each and every capacitor has those connecting wires that we will use to connect it in a circuit or wherever it is connected. What is a capacitor? I've already indicated that a capacitor is a device for storing an electrical charge and energy. What is it made out of? Capacitors are made. Some are made of contains at least 2 electrical conductors, as indicated, often in the form of metallic plates or surfaces. The plates are made of a conductive material such as aluminium, silver, and other metals. You know that metals are good conductors of electricity. These plates are each connected to terminals wire, which is what eventually connects to the rest of the circuit. Those terminals are indicated earlier on. Now, a standard capacitor contains 2 metal plates with an insulating material in between the plates. That insulating material, that's what we call a dielectric. Now, that insulating material is either made out of paper, glass, rubber, plastic, or anything that will impede the flow of current. Remember, I indicated that dielectric it does not conduct electricity readily. That is why it's an insulated, because it insulates. What is the purpose of the capacitor? To store energy in the electric field. It is much simpler than a battery, as it can't produce new electrons. It can only store them. A battery produces electrons and also stores them. A capacitor only stores the charges. What are capacitors used for? There are so many uses, as indicated earlier on, in house alarms, in electric circuits such as barriers to a lightning strike, storing a charge in an electronic flash camera, adjusting a tuned circuit such as a radio, used in microchips in the computer as well, capacitor banks in ESCOM. It also helps electrical motor to start, e.g. starter, or a motor of the swimming pool pump. They've got capacitors. And also we've got super capacitors to generate and deliver a huge amount of energy instantaneously. Like a charge capacitor has terminals. Like a cell capacitor has terminals. I beg your pardon. Inside a capacitor, the terminals are connected to a metal plate that are separated by an insulating material, which is called a dielectric. Now, let me explain what is a dielectric. A dielectric can be anything, e.g. air, plastic, paper, that does not conduct electricity readily, and it prevents the blades from transferring charges and touching each other. And okay, let me explain what will happen if these two metallic plates, if they get to touch each other. It means now they will transfer electrons, and now the current will start flowing, and it also can cause a short circuit. The bigger the area of the plate, the more charge the capacitor can store. This is the relationship of the charge between the charge and the area of the plate. So it means the bigger area will allow more charges to accumulate. And we can illustrate that by showing you what I mean by that. Now, if you have 2 capacitors, there's a distance in between these 2 capacitors. This is the area of one plate, area of another plate. And let me show you, okay, I'll try to have the same distance of separation. I'm keeping the distance constant. My drawing is bad, but you will get the gist of this. Now we've got two capacitors, capacitor 1 and capacitor 2. Capacitor 1 has small area, so it means it will accommodate or accumulate less charges as compared to capacitor 2 with a larger area. So capacitor 2 will accommodate more charges. Right. Now, example of capacitors. These capacitors are used in electronic and electrical systems. Here's an example of a capacitor. It's a parallel capacitor, parallel plates with area A and area B, which is equal and separated by a dielectric in between. As you can see, there's a distance of separation in between. There is a dielectric which now serves as an insulator. And we've got same thing happening to cylindrical ones. Now, how does a capacitor work? I'm going to take you through how it works, and lastly, I will show you how it's being charged. How do we charge capacitors? There are two conductors, and there are two conductors, and there is an insulator between them, as indicated in the slide before, called a dielectric. That is insulator between the two plates. The two plates inside the capacitor are wired to electric connection on the outside called terminals, which are like a thin metal legs you can hook into the electric circuit. Right. For you to understand how capacitors work, I'm going to take you through three experiments that I know it's just a visual experiment. You can do this on your spare time to check the validity of these experiments. Now, we have connected three capacitors in series on a circuit, and then we also connected a bulb. Now we check what happens. These capacitors are uncharged. So what happens to do you see anything? You won't see anything happening because the capacitors are not charged. Nothing is going to happen to the bulb. But let us move on to the next experiment. Same capacitors, and now we take out a bulb. We now connect a battery. We connect it for a while. What is a while? Until the potential difference of the capacitor of the capacitors is, if we connect a voltmeter reading across these three capacitors, if the voltmeter reading is equal to the voltmeter reading on the cells here, then your capacitors are fully charged. Then now, lastly, we take out, we disconnect the battery or the cells. We now connect back the bulb to the same three capacitors that were charged earlier on in experiment 2. Now, what you are going to observe, the bulb will now glow. Why the bulb glows? It means that because now we have disconnected the battery, but now the bulb glows. Since we have charged the capacitors, and the capacitors, remember we said a capacitor is an electric device. It's a electronic device that stores electrical charge and energy. So it means that the energy was stored after charging. There was energy stored, and now is being released to a bulb, and the bulb glows. This is how capacitors work. Another example that I can give for you to understand how capacitors work, let us say, for instance, you have a pump that pumps water. Water comes out into this well, then comes out. There's a flow of charges. This water will just flow into there. But when you close the water supply, the supply of water is no more. You are no more going to get any water supply in there. But if you were to connect this is a water pump with water coming through into this, and now you introduce water will be coming out at this end eventually. This will act as a capacitor in a way. I'm just trying to show you. You open water, there's a water flow coming into this big tent, flowing through the smaller tank, then outside. But now, what happens to the water supply when you cut off the water supply here? This small tank will still have a bit of water. If water runs out in here, the smaller tank will still have water to supply water, and the disturbance of water supply won't be that massive. Right, now how do we conclude? In conclusion, to explain how the capacitors work, when a capacitor is charged by a capacitor, the capacitor will store energy, and when the battery is removed, the energy will remain stored in the capacitor. And as the bulb is connected, the stored energy of the capacitor discharges and supplies energy to a bulb, which in turn glows. Right, now let us look at when you apply a voltage over the two plates, an electric field is created. Positive charge will connect to one plate, and a negative charge will be on the other plate. I'm going to show you this later on. In a way, a capacitor is like a battery, although they work differently as indicated. A battery will store and will also create a charge, whereas a capacitor will only store electrical charge. Now, symbols used. This is a symbol for a capacitor. Just an example of a capacitor connected in a circuit. When a capacitor is connected to a battery, the plate connected to a negative terminal of the battery accepts electron from the cell and becomes negatively charged, and the plate connected to a positive terminal loses electrons to the battery and becomes positively charged. Once fully charged, the capacitor has the same potential difference as the battery. The area of the metal plates determines how much charge the capacitor can hold, but the voltage depends on the voltage of the power supply that it is connected to. We will see this as we go on, how the capacitor is charged. Now, the capacitor is connected to the terminals of a battery as shown. There you go. Let me show this, let me draw this so that we have capacitors connected to a power supply. Right, we can maybe connect a voltmeter there, and also across the capacitors we can connect a voltmeter there. These are the capacitors. Now we can also maybe connect a bulb. Right, so what happens, this is how capacitors gets to be charged and acquire the positive charge and a negative charge. The current, when you connect the battery, current will flow from negative to, from positive to negative. So now A terminal that is connected to a negative will receive electrons from the battery. So it means now it will have excess electrons by accepting these electrons, and it will become negatively charged. The same applies to the other electrode or the other plate. The electrons will be attracted to the positive terminal of the cell. Then there will be deficiency of electrons on the plate. Then the plate will now acquire positive charges. Now the battery, the capacitor has now acquired positive and negative charges. If the power supply, it was maybe 6 volts, by the time, when we first connected the voltmeter, it did not record the 6 voltage. As it gets charged, eventually when it reaches 6 volts, it means that the capacitors now are fully charged and there is no more current in the circuit moving. Initially, when we start connecting the battery, the bulb will glow, but as time goes on, as and when the capacitors acquire charges, the light bulb will become dim until it does not glow at all, or it does not light anymore. So that is why I'm indicating that the current will now be 0. Remember, the potential, a high electrons move from a high potential energy to a low potential energy. That movement will occur until the capacitors are fully charged, and we will see that as and when the voltmeter reading reads 6 volts, as the same as in the battery, right? And then when that happens, there will be an electric field, external electric field between the plates, moving, the direction will be from positive to negative. Right, there we go. This is how capacitors are charged. The circuit, the plate connected to negative terminal receives electrons, as I've indicated, from the battery, and now it will have excess of negative charges, and eventually it becomes negatively charged. The same will apply to the plate, the other plate. The plate connected to a positive terminal will extract the electrons from the plate, and the plate will have deficiency of electrons, and hence it becomes positively charged, which leaves a positive charge behind, and a plate becomes positively charged. While a capacitor is charging, the electric current becomes smaller until no current can be observed in the circuit. Current equals to 0 now. When the capacitors are fully charged, there's no more movement of electrons. The light bulb will initially glow bright and slowly becomes faint until it does not glow anymore, since the current equals to 0 after the capacitors are fully charged. As soon as the current becomes 0, the capacitor is fully charged. The potential difference across the plates is then now equal to the potential difference of the battery, as I have indicated. This is the same picture that I've just indicated. And how will these, how will the capacitor acquire the charges, or how will they will acquire charges? The same as what I've drawn earlier on. Now the plate acquired positive and the negative charges. Then there exists an external electric field, as I've indicated. The external electric field, which its direction is from positive to the negative plate, the two parallel plates. The dielectric reduces the external electric field and retains the internal electric field in case where we have connected a dielectric. A short circuit will occur if two plates are brought together, and transfer of electrons will happen and the current will start to flow. Right, these are two graphs that shows the relationship between the current and time. Remember we said the current, when we connect a battery, we saw that the current was present because the bulb was bright, and as time goes on it became faint and faint until it burns out. So what does that mean? It means as time goes by, the current decreases until it gets to zero. Then a relationship between a charge, what happens, a graph for a charge, or a potential difference versus time while the capacitor is charging. Remember, when initially the charge does not have initially no charge, and as time goes on the charge increases until the current is zero. Right, these are the two graphs indicating the relationship of current versus time and charge versus time. Now these are the parallel plates and the capacitor. You have seen this before. Right, now this is a drawing that shows an electric field line patterns of a parallel plate. We've got two parallel plates. One plate is positively charged, it's on top. At the bottom is a negatively charged plate, and there are field parallel, there are field lines across. Those are electric field lines pattern of parallel plates. Direction, they are moving from positive to, is moving from, the field lines direction is from positive to negative, indicated by arrows. Right, different types of capacitors. With the dielectric material determines the type of a capacitor, the material used as an anode, and to construct and the construction of the cathode of the electrolyte. The most common capacitors are ceramic capacitors. We also have plastic capacitors. One type that is mostly used, or that is generally used, is a ceramic one, because it is of a superior quality than the others. Some capacitors are polarized. They can only be connected one way, and electrolytic capacitors are polarized. These are the example of these electrolytic capacitors. We also have variable capacitor. Remember earlier on I've indicated a fixed capacitor. I've shown you how we show a fixed capacitor and a variable capacitor. Now variable capacitors are used in communication equipments, radio, television, and VCRs. They can be adjusted by consumers by tuning controls. Now we've also have trimmers. These are internal adjusted capacitors that you cannot adjust by yourself. These are the pictures and examples of these capacitors. Right, let us answer the few questions just to check our understanding. Which one of the following is equivalent to the unit of capacitance? Remember earlier on that we are given CV. We've got also CV to power negative 2, CV to power negative 1, and CV squared. Right, when we started with this lesson, I indicated to you formulas to calculate capacitance. We see capacitance is equals to charge over potential difference. And we said capacitance is calculated in farads, then charge in coulombs, potential difference in volts. Right, so it means 1 farad, 1 coulomb, 1 volt. Therefore, now let us check. These two will be equals to CV. This is the same as CV to power -1. Right. So it means now, can you see? Let us go back and check the possible answers. Which one of the following is the equivalent unit? Which is the equivalent unit to Farad? It's C. It's coulomb per voltage per volts. Coulomb per volts. So the correct answer there is C, which is now it's the equivalent SI unit to Farad. It's the same as it is equals to the Farads. There is the answer. The second question that we look into is capacitors. A capacitor stores charge Q at a potential difference of V. What will happen to the magnitude of the charge if the potential difference is doubled and the capacitance is kept constant? The charge will be Q squared, remains Q, will be half Q, will be 2Q. We are not going to guess the answer. Let us check this. Let me just write first the capacitor. Okay, there we go. What will happen when we double what? The potential difference. Right, let me show you this. From the same formula, C equals to charge over potential difference. They say now capacitance is kept constant, the charge is kept constant, maybe it's 1, 1. Then what will happen if we double the potential difference? Charge will be CV. Charge will be CV when we make charge the substitute formula. Therefore, charge will be equals to capacitance is kept constant is 1. We substitute the value for potential difference, which is 2. Q equals to 2. Therefore, it means this is 2Q. Let us check which answer is correct. The correct answer will be D. And this is how we have calculated, we have proven that it is D. It means a capacitor, when you double the potential difference, you also double the charge. So it means they are directly proportional. Right, now let us look at examples of capacitors used in technology. We've got film capacitors, which are electrical capacitors that contain an insulating plastic film, which is the dielectric and sometimes combined with paper as a carrier of electrodes. The paper and the metal strip are rolled into a cylinder, forming a large area of metal separated by a wax as the dielectric. These capacitors are very cheap. They make good general purpose capacitors. Often plastic capacitors such as polycarbonate and polyester are used instead of paper as they improve the frequency response. Right, these are examples of capacitor electrolytic capacitors. There is a thin strip of material which is rolled into a cylinder to form a large area in order to maximize capacitance. Remember, large area equals to greater capacitance. Less area or small area will give less capacitance. The dielectric used is just a thin film of aluminum oxide formed on a positive strip of an aluminum foil. Now, the chemical reaction forms the oxide layer. It may be less than 10 to power -6 meters thick. Greatly increases the capacitance. Right, now This is just a whole story about example of capacitors used in technology. We also have variable air capacitors. Tuning circuits require a capacitor whose value can be changed. That's why a variable capacitor will be useful in this instance. Like our remote controls will have a variable capacitor so that we can tune. Radios also have a variable capacitor so that we can tune them whenever you want to tune them. Now, capacitance is the ability of a capacitor to store charge. The bigger the potential difference across the plates, only a specific amount of charge can be stored. It is said to be it is said that the capacitor has a fixed capacitance, so it has a fixed value of charge that it can acquire. Capacitance of a capacitor is defined as an amount of a charge it can store per unit volt. Right. The bigger the potential difference across the plates, the bigger the charge on the plates. This means a charge on the plate is directly proportional to the potential difference across the plates. Now, this proportionality between the potential difference and the charge can be expressed as follows. Q equals to CV, so that we know that capacitance is Q over V. This formula is used to calculate capacitance of a capacitor. Remember when we started, I've shown you all the formulas that we're going to use to calculate capacitance. We know C represents a capacitance of a capacitor measured in farad. Q a charge, we measure that in coulomb. V stands for potential difference, which we measure in volts. Right. The unit of capacitance is named after the English scientist Michael Faraday, where 1 farad equals to 1 coulomb over charge. Thus, 1 farad equals to 1 coulomb per volt. Remember the other formula, we said SI unit, which is equivalent to farad. There it is 1 coulomb per volt. This means that the capacitance of 1 farad, if it is stored 1 charge when a potential difference of a capacitor is 1 volt. The practice, in practice, the farad is extremely very large value, as indicated earlier on. Then we will use. We usually indicate smaller values like in smaller values, microfarad. We know that a microfarad equals to is a factor of 10 to power negative 6. A nano is 10 to power negative 10. So it means whenever you are given a value in microfarads, you need to multiply it by I beg your pardon, by 10 to power minus 6, nano 10 to power minus 9, picofarad by 10 to power minus 12. Right. The capacitance of a capacitor is constant for a given capacitor. It is determined by a relationship of a charge over potential difference, and it does not depend on or not dependent on a charge and potential difference. It merely indicates how much charge can be placed on a plate to obtain a specific potential difference between the plates. The bigger the capacitance, the more charge can be loaded on the plate. Right, these are just the very same values I've indicated of microfarads, what we need to multiply it by to convert it to farads. Right, here's an example. A parallel capacitor has a potential difference of 100 volts between the plates. Each plate carries a charge of 1 times 10 to power negative 5 coulombs. Calculate the capacitance of the capacitor. Step 1. we check all the information that we are given, all the data that we are given. We are given potential difference 100 volts, we are given a charge, we need to calculate for capacitance. So we use the formula for capacitance, C equals to Q over V, then we substitute. These values are given in a correct SI unit. We do not need to convert. So a charge, we substitute it as 1 times 10 to the power negative 5 divided by 100, which will give, in turn give us 1 times 10 to the power negative 7 farads. Right. Now let us check this activity. Define a capacitor. Remember, a capacitor is an electronic device that stores energy. That is 7.2 there. Then let's check the next question. State the relationship between the capacitance and the charge on the plate. Now the relationship will be the capacitance is directly proportional to the charge between the plates, or we can indicate that as C is directly proportional to Q. Capacitance is directly proportional to the charge between the plates. That is the relationship between the two. Now, the last question, state 2 changes that you can make to a capacitor to decrease the capacitance. Right. We can decrease the surface area, remember, but when you decrease the surface area, the distance between must be kept constant. Then when you decrease the surface area, it will decrease the number of charges that can be accommodated on those capacitors, on those plates. Or also increase the distance. Now when you increase the distance between the plates, keeping the plate or the area the same, then that will reduce the capacitance. The more far apart the plates are placed, the less capacitance. It means the electric field force will be less between the plates. When you decrease, that will increase capacitance. Or we can use a dielectric material with a low dielectric constant permeability. These are the things that you can do to decrease capacitance between the two plates. Right, these are the solutions. Right, let us continue with the examples. Name 2 factors that will affect capacitance. We've just mentioned the opposite those factors. It's in the surface area of the capacitors. The larger the surface area, the more capacitance. The smaller the area, less capacitance. Also, the distance between the plates. When you keep the area constant and decrease the distance between the plates, that will in turn increase capacitance, or that will affect, the distance will affect the capacitance, the type of a dielectric material, because dielectric material have different permeability values. Right, some more activities. The first one, define the term capacitance. We know that capacitance is the charge stored in the potential of in the plates of the capacitor per unit potential difference between the plates. Right. Now we have a question there. A capacitor stores a charge Q at a potential difference V. What will happen if the potential difference between the plates of the conductor is doubled? Right. Possible questions. Capacitance falls to the half of its original value while the charge remains the same. Both capacitance and the charge fall to half their initial values. Both capacitance and the charge doubles. Capacitance remains the same, and the charge doubles. Let us read the question again. A capacitor stores a charge Q. What have I done now? Right. Let me go back. A capacitor stores a charge Q at a potential difference V. What will happen to the potential difference between the plates if a capacitor is doubled? The formula, remember, the formula to calculate capacitance is C equals to V over Q over V, charge over potential difference. Now, the capacitor is kept constant and the charge is kept constant. We double the potential difference. So we want to know what will happen to the charge. Capacitance will be half the value of the potential difference. The capacitance will be half the value because all we do is, from the formula, C equals to Q over V. This is kept constant, and we double the potential difference. Now C, capacitance will be now halved. Capacitance will be half because we have doubled the potential difference, and that also gives us the relationship between the capacitance and the potential difference. And go back. Now let us look into the second one. Number 3 there. If a charge of 1,2 microcoulombs are placed on a plate separated by a metal plate, the potential difference between them is 11,3 volts. What is the capacitance? Right. Let us do this calculation. We are supposed to calculate the what will be the capacitance. Capacitance is given by a formula C equals to Q over V. So I'm not going to show you when I do calculation because I don't want to lose the values there. Now, if the capacitance, let us check the values. We are given a charge, but we are given the charge in microcoulombs. So we are going to substitute charge as 1,25 times 10 to power negative 6. Remember, that's what I said, that you must convert to a correct coulomb. We given charge as a coulomb, but you must convert it to microcoulombs, divided by potential difference of 11,3 volts. So that will give us 1,11 times 10 to power negative 7 farads. This is the capacitance of these two plates. Now let's look at number 2 as well. Question number 4. A capacitor has a capacitance of 7.28 microfarad. What amount of excess charge must be placed on a plate for its plates to make a potential difference between the plates equals to 225 volts? Same formula, C equals to Q over V. This time around we are given capacitance, but we are given capacitance as microfarad, so we substitute it as 7,28 multiplied by 10 to power negative 6 equals to what are we given? We are given the amount of access charge placed between. Okay, we must now calculate. We want Q. We substitute V, which is the potential difference, which is 25. Therefore, Q equals to 1,82 times 10 to power minus 4 coulombs. There you go. If you check at the response, we always must convert the values to the correct SI unit. Now let us check at question number 5. Determine the charge stored on either plates of 4 microfarad parallel plate capacitor when connected to a 12-volt battery. Now we must calculate for a charge. C equals to Q over V. We are given capacitance 4 microfarad, so it's 4 multiplied by 10 to power negative 6, equaling to Q divided by 12 volts. Therefore, our Q is going to be equals to 4 multiplied by 4.8, 4,8 times 10 to power negative 5 coulombs. Right. These are the examples. Let us move on. Okay. This examples and activities brings us to the end of the first session. The next session we are going to pick up with calculations of parallel plates now. Okay, thank you.